let us start with exercise 8.5. Let's try few questions from 8.5. So let's try our question number 6. So what we have in a question number 6, we given a series this. We need to check whether this series is convergent or divergent. Now we're going to use the comparison test because the exercise is based on the comparison test, maybe limit comparison test and a direct comparison test. Now you can directly see that what would be the choice of Bn if we want to apply the limit comparison test, since your An is n plus 1 upon n square and n. So as we have discussed, in these cases it is the difference of the power of denominator and the power of numerator, and highest difference of the highest powers. So if you see that you have 5/2 power in denominator and 1 in numerator, so you choose Bn to be 1 by n raised to power 3/2. Now, so for limit comparison test, you take limit n tends to infinity An upon Bn, limit n tends to infinity n plus 1 n by 5/2 by 1 by n raised to power 3/2. So it would be limit n tends to infinity n plus 1 by n by 5/2 into n 3/2. Right. So if you cancel these terms, what do you get? Limit n tends to infinity n plus 1 by n. Right. So it becomes 1 plus 1 by n. Let me directly write it as 1. Now this is what? Non-zero finite. So what our comparison test says, that in this case summation An and summation Bn behaves alike, right? So if they behave alike, but we know that this series summation Bn is convergent. Why? By p-test. By p-test, because your power is greater than 1, that's why it is convergent. So therefore summation An is also convergent. So that's what we wanted to show, so whether it is convergent or divergent. So now next is so let's say question number 9. So now you have n runs from 3 to infinity 1 by log of n. This is slightly tricky, right? So where to compare with the log n? Log n can be compared with n. You know that n grows more rapidly than log n, so we know that our n is always bigger than log n. So now log n is, if you take log on both sides, so log n is bigger than log of log n, right? Let me put it over here. So if you compare these three things, so you compare these two inequalities, so we can write it as n is greater than log n and log n is further greater than log of log n, right? So you take reciprocal, so 1 by n would be lesser than 1 by log n and would be lesser than 1 by log of log n. Now you just drop this thing and take the relation between these two. So that means you simply write it as this way. So now you want to decide the convergence or divergence of series based on this an, right? But this is already bigger than a series which has to be divergent, right? So now, since summation 1 by n is divergent as it is harmonic, therefore by direct comparison test, summation 1 by log of n is also divergent. So next is question number 15. We wanted to check the convergence or divergence of this thing, right? So as I've told, your log n can always be compared, most of the time your log n can be compared with the n, 1 by n. So you can do that. How? So your an is 1 upon 1 plus log n, and take your bn to be 1 by n, right? So now consider an by bn. So this becomes 1 upon 1 plus log n upon 1 by n, which is n by 1 plus log n. Now you take limit on both sides. Limit n tends to infinity, n upon 1 plus log n. So since take differentiation, so differentiate numerator and you differentiate denominator, right? So it becomes limit n tends to infinity n, which is infinite. Now you know that in case of infinite, if summation bn is divergent, then summation an is also divergent. And we know that also summation bn is divergent. Why? Because again it's a classical harmonic series. So therefore summation 1 upon 1 plus log n is also divergent. Question number 16. I'll give you the hint. So for this question, again you need to choose the bn to be 1 by n, and you use the direct comparison test. So it will come out to be a divergent series. Similarly, for question number 18, you have summation n runs from 1 upon 1, summation n runs from 1 to infinity, 1 plus log n square. In this case too, you should choose bn to be 1 by n, and then this will also be a divergent series. So these are the hints for question number 16 and question number 18. So next is question number 23. So this is n runs from 1 to infinity, 1 upon 3n minus 1 plus 1. Now this is something which is very easy. So your an is 1 upon 3n minus 1 plus 1. So this is of course less than if we keep 1 minus 3 raised to power 1 minus n alone. Why? Because the denominator has decreased, so that's why the quantity will be bigger. So now, but you know that this bigger series is always going to be convergent. Why? Because this is GP, right? So, but summation this is convergent as it is a GP with common ratio 1 by 3. So therefore summation an, which is equal to 1 upon 3n minus 1 plus 1, since your summation an is, by direct comparison test, it is also convergent. Number 24 is something like that. N runs from 1 to infinity. See, most of the time the nth divergent test is the thing which generally hard to recognize, right? So you always try to, most of the times if you are not able to see that whether it is going to be convergent or divergent, then trying that nth divergent test is worth. So that it is the necessary condition that this thing should be 0. So let's check it first. So this becomes 1 by 3n. So if you divide it, you are left with 1 by 3 plus 1 by 3n. So now this becomes 1 by 3. So which is not going to 0. So therefore by nth term divergent test summation n runs from 1 to infinity 3n minus 1 plus 1 by 3n is also divergent. So next is question number 29. N runs from 1 to infinity tangent inverse n upon n raised to power 1.1, right? So that tangent inverse n is always going to be less than pi by 2, right? Why? Because that tangent inverse infinite, it takes the maximum value at pi by 2. So now if you divide both sides by n raised to power 1.1, why? Because this is the expression, this is the quantity we need over there. That's why we are dividing this. So now this is your an and this is your bn. So by comparison test, we can apply the comparison test over here. If your bn, summation bn is convergent, then your summation an is also convergent. But what about this one? What about bn is convergent? Why it is convergent? Because that you can take pi by 2 outside, and this is something which you have is convergent by p test, as it is greater than 1. No matter how how small the difference between 1 and this, if this is on the larger side, definitely it will be convergent. Now your bigger series is convergent, so as we have discussed, so therefore by comparison test your smaller series is also convergent, right? So that's the thing. So similarly you can do the question number 30 as well, right? So let's do some more questions. Let's say question number 32. So this is summation n runs from 1 to infinity tangent hyperbolic n by n square. So you want to discuss that whether it is convergent or divergent. So you know that already n square is over there, so let's choose Bn to be 1 by n square. So now all you need to find out, limit n tends to infinity an upon Bn, limit n tends to infinity tangent hyperbolic n upon n square by 1 by n square. So this will be cancelled. So limit n tends to infinity tangent hyperbolic n, which you know that can be written as en minus e minus n en plus e minus n, right? This is the expression for the tangent hyperbolic n. So now divide numerator and denominator by e raised to power n. So you get 1 e raised to power minus 2n, 1 e raised to power minus 2n. So as your n tends to infinity, right, so e raised to power minus 2n, since this is reciprocal, so it will go to the 0. So you are left with 1 minus 0 upon 1 plus 0, which is nothing but 1. So this quantity is coming out to be 1. That means non-zero finite. So by comparison test, therefore by comparison test, limit comparison test actually, if summation Bn is convergent, or I should write it more properly, summation An and summation Bn behaves alike, but summation Bn, which is 1 by n square, is convergent again by p-test. Why? By p-test, right? So therefore summation An is also convergent. Question number 37, A part. So its A part. It says that you need to write the proof of all those remaining parts of the limit comparison test. So let's write the proof of them. So the remaining proofs were, if limit n tends to infinity an upon bn is 0, then we need to prove that if summation bn is convergent, then summation an is convergent, right? So let us try to use this thing. So this is a sequence which is converging to 0, right? So by definition, so therefore for every epsilon positive, however small, there exists m belongs to the n defender such that the difference between the sequence and the limit, this is your sequence, this is your limit, right? So this difference can be made less than epsilon for all n greater than equal to m, right? So from here I can write it as minus epsilon to plus epsilon for all n greater than equal to m, right? So minus bn times epsilon and an times here epsilon times the bn for all n greater than equal to n. This equation, now you may take the right hand part of this. Now you will come to know that, see, so if you take the RHS right side of inequality, so that was what? So your an is less than the epsilon times the bn, right, for all n greater than equal to m. So that means by comparison test, right, So let me put it like this. Therefore, by comparison test, if summation Bn is convergent, then summation An is also convergent. Right, because epsilon is constant and it can be taken outside. Now a natural question arises that, you know, in the last ratio test and root test, even in these tests, we have also selected the left hand part of the inequality, and it was working fine when we used to have a non-zero number over here. But when the non-zero number is replaced by 0, then only convergence will imply, not the divergence. So why divergence will not work? Let us see. So let us see what is the problem in the left hand side of this inequality. Now if you see that, so let me put it under note. So if you choose the left hand side, if you choose left part, so you actually say that your minus b in epsilon is greater than your less than your an, or let me put it in other words, that your an is greater than minus epsilon times the b. Now you see that this is something which is inconclusive. Why? Because if your bn is divergent, let's say it goes to infinite, and a minus is over there, so that becomes minus infinite, right? So you will conclude that your summation an is greater than minus infinite, which is something which will not, you know, this statement will not enable us to make a conclusion about this. Why? Because since your ans are positive, right, so your summation an will always be positive. So if it is finite, even then this thing will true, and if your summation an is divergent, even then it will becomes infinite. So that is also again true, right? So in both the scenarios, this inequality, the above inequality, this inequality will not conclude anything for us. Why? Because it gives us an idea that summation an is greater than minus infinite, which can be satisfied by two things, right? Either its summation an may be finite or summation an may be infinite. So we can use both the cases over here. So we cannot choose a proper case out of this, that whether summation an is divergent or convergent, we cannot make any statement over here, right? So that's why we would say that the left hand side of this inequality will not work. So let us understand with the help of an example as well. So let's you take an example, your an to be 1 by n square and your bn to be 1 by n. So now if you take an by bn, it becomes 1 by n square by 1 by n. So you take limit n tends to infinity en upon bn, which will be let me put it over here, which will be limit n tends to infinity 1 by n, which is 0, right? So now it is 0. Now you say that your summation bn is what? Summation 1 by n, which is what? Is divergent. Now you take another example where you take an to be 1 by n log n and your bn is 1 by n, right? I should write it more properly before taking to the next example. So but what about your summation an? Your summation an is 1 by n square, which is convergent, right? So now again you take summation bn. Now again you make an upon bn, that means 1 by n log n upon 1 by n, which would be 1 by log n, right? So now again if you take limit n tends to infinity an upon bn, which is limit n tends to infinity 1 by n log n upon 1 by n, so which is 0, right? So now if you see that, now again, but your summation Bn is divergent. But what about summation An? That is summation 1 by n log n is convergent. How you prove it? Is divergent. How you gonna prove it? You can prove it by using the integral test, right? How you can do it? So let's say your f of x is 1 by x log x, and let's say you start from 2 to infinity because log 1 is 0, right? So now by integral test you choose it like this. Now put log x is equal to t, so 1 by x dx is dt. So if your x is 2, your t is log 2, and if your x is infinite, your t is infinite. So we will write it as 2 to log 2 to infinite 1 by t dt, right? And this is nothing but log t 2 to infinite, which is nothing but infinite, right? So we have proved that summation An is divergent. Now you see we have constructed two cases. So in one case, this your An by Bn, you take limit An by Bn and it will come out to be 0, right? So in second case as well, let me mark it over here. So this is your case 1, this is your case 2, right? So in second case also you have chosen An by Bn such that your An by Bn, if you take limit n tends to infinity, so it will come out to be 0. But and in both the cases you have chosen summation Bn such that it is divergent. Okay, so let me mark properly. This is your Bn. In both the cases it is divergent. But you see that in first case we have constructed such an An where your summation An is convergent, but in second case your summation An is divergent. So that means you cannot conclude anything. It may be divergent or it may be convergent. So that's why you can prove only one part. You can choose only this right side inequality. The left hand side inequality will not work in case when your limit n tends to infinity, An by Bn is 0, right? So that's what I want to prove. Question number 38. Now you have n runs from 1 to infinity, En is convergent, so with such that your Ans are positive, right? So we want to make some conclusion about the summation An by n, right? So your n runs from 1 to infinity. So can we make some conclusion? Yes, we can definitely make such conclusion. Why? Because you know that your An by n is always less than the An. Why? Because in denominator we have the least value 1 for all n. So therefore by comparison test, summation An is convergent, then summation An by An is also convergent. Question number 40. What it says? Say that, show that if summation An is a convergent series, of non-negative terms then summation an square converges. That's what we're going to prove. Given that summation an is convergent, so if it is convergent, then it must fulfill the necessary condition, which is limit n tends to infinity an has to be 0, right? So what does that mean? That means the difference of an and 0 can be made as small as we want, right? So that means for every epsilon positive, however small, there exists m belongs to n such that your an minus limit, which is 0, can be made less than epsilon for all n, for all m n greater than equal to m. So that means your mod n can be made less than epsilon for all n greater than equal to m. So you simply write it an, right? Why? Because an is a positive, that's why, for all n greater than equal to m. So you can multiply both sides by an, so it becomes an square is less than an epsilon for all n greater than equal to m. Now you see that now this inequality can be used to apply the comparison test, right? So you see that it is given to us that summation an is convergent. So if summation an is convergent, then of course epsilon times summation an is also convergent. So if it is epsilon time of summation an is convergent, then the smaller series, that is an square, which is also convergent. So that's how we're going to use it. Now since summation an is convergent, therefore epsilon times summation an is also convergent. Therefore by comparison test summation an square is also convergent. So let me put a bonus question over here. I would say that the converse of this statement will not hold, right? So note converse of question number 40 does not hold. That's what? If summation an square is convergent, right, given an's to be positive, then summation an may not be convergent, right? Put me in a, then summation an may not be convergent. So for this I'll pick an example. That's what, take an square is equal to 1 by n square. Now you know that summation 1 by n square is convergent by p-test, right? But if you take summation an only, that means it becomes 1 by n, you take the square root, summation 1 by n. So this is harmonic series, which is what? Divergent, right? So the converse of this question number 40 doesn't hold, right?